Hello guys, welcome to Chess Programming Crash Course. This tutorial is inspired by NegaMax chess engine by Muller, who has created one of the smallest chess programs in existence. Here on his side there is a great tutorial covering the most basics of chess programming in general and the algorithms implemented in NegaMax in particular. But when I followed this tutorial a couple of years ago, I considered it to be a little bit too complicated for beginners, and that's the reason for creating this sort of video where I've simplified the concepts presented in NegaMax in even more simple way. Also created this experimental Python development environment for you guys to follow this tutorial completely in browser. So no need to install any programming languages or compilers or any dependencies on your local system, so you can type code here online and see the output and just follow the tutorial in an easy way. Also, please don't be afraid of Python itself. If you don't know Python, it's not a big deal. I'll try to write code as language agnostic as possible. So if you're excited, let's actually start writing some code. The very first thing to consider is to define the piece encoding. So let's actually do this now. So piece encoding. And here I'll be using both binary and decimal representation of the piece codes. So let's have binary 001, which would be equal to decimal 1, and this would be the white pawn. And okay, and then 010, this would be the decimal 2, this would be the black pawn. And you might wonder why the white and black pawns are different piece types, but this is NegaMax engine specific, so just bear this in mind. And the next piece to consider is actually 011, which is decimal 3, and this would be a king regardless of color. And then 100, which is decimal 4, it would be the type of knight. Then 010, which is 5 in decimal, this would be type of bishop. Then 110 is decimal 6, the type of rook. And finally 111, decimal 7, a type of queen. Also, we will be used the 8th and the 16th bit to represent white and black color respectively. So this would be decimal 8, so this would be the white color, and this respectively 16 here, this would be the black, this would be the black color. So now in order to obtain the piece code, we need actually to bitwise OR the white color with piece types and the black color with piece types as well. So let's actually do this now. So in order to obtain the piece codes for the white pieces, we need to bitwise OR this 8 in binary in the representation. 8 looks like this with white pawn here, so 001. And if you're not familiar with bitwise operations, please check those out, because otherwise it would be hard for you to understand what's going on here. But in order to, so I'll be calculating this manually. So this would be 1001, and in decimal, so let me just show you how to convert the decimal number to the binary number to the decimal. So this bit is worth 1, this bit is worth 4, this 8, this 1, 2, 4, and this 8, and this one worth actually 16. And in order to convert this binary to decimal, we need to add the value of each bit all together. So here it would be 8 plus 1, so this bit is worth 8, this one worth 1, so 8 plus 1 would be equal to 9. So we have the 9 in decimal, and this would be white pawn. So while this white pawn is not actually the white pawn, but this is just kind of pawn that is going upwards, so we can specify it like this. And this is basically the pawn is going downwards regarding the board. But so if we want to obtain the real piece code for the white pawn, actually, so we need to bitwise and this piece type with this color of white. So this is the binary representation of 8, number of 8. Now let's move on doing the same for the rest of our pieces, actually. So the second thing to consider would be actually a queen. Would be a king. So 0, 1, 1, and this would be respectively like this. So we'll just bitwise OR these two numbers. So let's calculate. So 8 plus 3, and this would be 11. So the 11 would be the value for white king, and then absolutely the same for all the rest of the pieces. So for 1, 0, 0, and 0, 1, 1, 0, 0, this would be 8 plus 4, which is equal to 12. This would be the white knight. Okay. Also, so this would be equal to 13 respectively. This would be the type of white bishop, and so this would be 14, which is the type of white rook. Okay. And this one would be 15 respectively, and the type of white queen. Now let's do absolutely the same, but for the black pieces. So in order to obtain the black pieces piece codes, we need to bitwise OR the 16th bit, so the number of the 16. So this number in decimal would be equal to 16. So we need to bitwise OR this starting from the black pawn type and going further in. So here is 0, 1, 0s, and this would be equal to 0, 1, 0, and so 16 plus 2, it would be equals 18. So 18 would be the code for the black pawn. Okay, and now the king is 3 here, so 0. So 16 plus 3 would be 19 respectively. Okay, so this would be the white king. Here we have 16 plus 1, 2, 4 plus 4, so this would be 20. This would be the white knight. And respectively 21 for white bishop. And okay, 22 for white rook, and $23 for white queen. Oh, sorry guys, of course not the white but the black pieces here, so just let me quickly change this to black. Of course, these are the piece codes for the black pieces. And now when we have our piece codes, it's actually time to define our board, and in order to do this we'll be using what is known as hexadecimal 88 board representation, which is the array of 128 elements. So it's gonna double 44 plus 44 squares, so one on the left, one on the right. So let me basically show you this so you'll easily understand kind of how this board representation works. And some magic behind this representation will be covered later on in this video. So now we need basically to set up our pieces on the board. So in the top left corner we will be having the black pieces. So there it starts from the rook, black rook, so it would be the 22, and then goes black knight apparently, yes, so 19, and then black okay, so black knight is 20, sorry, so black knight is 20, then black bishop, that would be 21, and then black king, okay, it's black queen, no, black queen, so 23, and then the black king is 19, and then again the bishop, the knight, and the rook. Okay, and the right part of the board would for now be just 8 zeros, but later on this 1 2 3 4 8, okay, but later on this kind of elements would serve as the scores for the evaluation function. So it would represent the score that piece is going to gain if it stands on the particular square. So just that would be covered a little bit later on. And now the black pawns. So the black pawns are 18. So here we have 18, 18, 18, 18. Okay. Okay, then it would go just the zeros for the empty square. So I just forgot to say that 0 does represent the empty square here. Okay. Okay, so now we can just copy this sort of stuff. And here we have the white pawns. So the white pawns is 9. Okay, so 9, 9, 9. Of course, I could have copy-pasted this from the source that is already written, but I just want to make everything by hands, guys, so you will for you to understand every single part of this program of what's going on here. So okay, and now the white rook. Where is the white rook? It's 14. 14. Then white knight, 12. A white bishop, 13. Then the white queen is 15. White king, 11. And again, so the bishop 13, knight, and the rook, and the rest would be zeros. So he'll write a little commentary. So board representation, and okay, plus piece square scores. So for now we didn't yet initialize our piece square scores, but we'll just leave this for the commentary as well. And another thing to consider, so now imagine that if we're supposed to print this board to screen and we would see all this kind of numbers, it would be really difficult to debug the program. So it would be really nice to have somewhat user-friendly, somewhat more user-friendly piece representation. So in order actually to obtain that, we'll need to make a couple of tricks. But also not only the piece representation but the square representation as well would be needed for us. So like when we will be generating our moves, say this pawn going from this square to here, so the indexes of this board array won't really tell us much, so it takes ages to understand what's the from square for the pawn and what's the to square. So it's really nice idea to map squares to the indexes, and in order to do that we need to create a notation array here which would specify the names for each particular square. So that would be needed during the move generation time. So starting from A8, and then we go in for B8 and C8, okay, and D8, A, B, C, D, E8, F8, G8, H8, okay, and we can just we could have probably defined the values for this squares as well, just for the debugging purposes, because if it happens that the piece would go in out of the board, which is not really that possible in this implementation, but still it's kind of pretty nice for the debugging purposes to have the names for this sort of squares. So let's actually define them as well. So H, okay, H, J, oh my god, I forgot the English alphabet. A, B, C, D, E, F, G, H, I, J, K, H, I, J, K, L, A, B, C, D, F, G, H, I, J, K, L, M, N, O, and B. Okay, so K, L, M, N. So 1, 2, 3. What's going on with my mouth? 1, 2, 3, 4, 5, 6, 7, 8. Okay. O, P, and all the 8s respectively, of course. So okay. Great. And now we can just copy and paste it 7 times. So 1, 2, 3, 4, 5, 6, 7, 8. So this one would be changed to 7. Okay, let's maybe better make it 7, 6, 5, 4, 3, 2, 1. 7, 6, 5, 4, 3, 2, 1. Okay, let me just pause the video and do this stuff. So finally we have our notation array being initialized, and now it's time to define the print board function. So in order to do that, I need to say def print board, and here I'll define the index variable, which would be held in the current square we are iterating over during the loop. So it would be equal to 0 first, and then we say while index is less than 128, which is the length of our board array. So bearing that in mind, please. As far as I'm trying to be language agnostic here, I'm not specifying the this sort of like LAN board, which is Python specific. So that's just hard code. Let's just give this hard coded 128 instead. So we need to increment our index by 1, and let's actually print our index. So in order to run the function, of course, we need to call it first. So I say print board and hit Control-Shift-Enter to execute the code. So by default, Python would print any new variable from the new line. So in order to avoid that behavior, so some little Python specific stuff is needed here. We need to specify the end equals to a space, and here we have all the stuff printed in one line here. So now some magic behind the hexadecimal 88 board representation, which is the name of the board representation itself basically. So if we want to answer the question whether the particular square is on board, so I mean here, or is off board, we can use the only bitwise operation. I'm not going to dive into the deep explanation of how it works. Instead, I will just show you how to make use of this sort of property. So we need simply to say if index bitwise end with the constant of hexadecimal 88, or in decimal this would be the number of 136, well, but it's better to use the hexadecimal 88. And if this equals to 0, well, in this case, let's actually try to print our index. Just execute the code one more time, and here it's not really that explicitly clear that we've just printed only this left part of the board. So to make it more clear, let's actually make use of our notation array indexed by the square. So here we see that we're only in the left part of the board. And now what we need to do here and here and so we need to add basically new lines. So in order to implement that, let's do the following stuff here. So we'll use index plus equals 1, so incrementing index by 1 in case if we are on board. So here we'll say square is on board, and otherwise we'll do the following stuff. So we can simply say else, and here we want to print well, so just if we just call the print without providing anything, it would by default print the new line in Python. So in whatever other language you would probably need to print a new line like this, but in Python it's enough just to print, and that's it. And also we need to skip the indexes so we need to skip these indexes. So we don't need to print the new lines over here. So in order to do that, we need to increment index by 8, not by 1, like this. And here, okay, something wrong with the indentation levels. Just hold on a sec, guys. Okay, now it works. So in Python it's important. So here I had tab instead of spaces. So if you're using tabs, then use the tabs. If you're using spaces, use the spaces. So that's important. Otherwise you'll get that nasty indentation errors. So here we have our squares printed in the more like a board, printed like in a form of a chessboard, which is already pretty nice. But we don't really need our square names. Instead we want to have our pieces. So let's actually type the board indexed by the square, and here we have our pieces. So what we're supposed to do now is actually to map these piece codes to somewhat letters representing our chess pieces. So let's define the pieces variable of the type of Python string, which would serve us as the mapper of our piece codes to the letters. So let's see what we got in our encoding. So we'll start with the empty squares. So here we see that the zeros representing the empty squares. So we'll use the very first index of the pieces array. So pieces, I mean, like if user calls pieces 0, this needs to return an empty square and character for the empty square. So in our case this would be this dot here. So we'll be using our piece codes, not the piece codes themselves, but the piece codes bitwise ended with 15 to extract the particular piece, and that would return us the index retrieved in that sort of way would be used to index our pieces in order to map our piece codes to the ladders, and it's really easier to actually to do rather than to explain. So let me just quickly do this, and then you'll understand of what's going on here. So then it would be so we'll start with the black pawns. So we need to, so as far as the black pawn is the number of 2, so we need to skip one index here. So dash in this case is just a placeholder, and then we have our pawn, and basically king, pawn, yes, king, knight, bishop, rook, and queen. Okay, so then we don't have the index of 8 and any piece of number of 8, so we just skip this. Then we have the white pawn. Okay, white pawn, then we skip again because this would be the black pawn, so but we already used that sort of code. And now actually king, knight, bishop, rook, and queen, like this. Okay guys, so let me just first show you how this is supposed to work, and then to go for a little bit of explanation of how it works. So we can reference the pieces array indexed by so board index is actually our piece. So well, let's actually create, for more clarity, let's create our piece variable here that would be equal to board index, like this. So okay, so piece bitwise AND with 15 to extract the first 4 bits of the particular piece. So, and I hold my breath and run this stuff, and suddenly we have our pieces mapped to the corresponding ladder. So the uppercase represents the white pieces, so pawns, rook, knight, bishop, queen, king, bishop, knight, rook, and the same for the black pieces. And now let me dive into a little bit into the logic behind this little trick. So what is the piece? So the piece is actually say this number. So this is 9. Okay, so if we have 9 in the binary format, let me quickly show you that. So let's have, so this is 9 in the binary format here. So this bit was 8, this was 1, so 8 plus 1 equals to 9, and this is the type of the white pawn. So this number serves as the index in this array. So let's calculate. So index of 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Here we have a white pawn, and say okay, so but actually the white pawn is not okay. So white pawn is actually 9. So this is kind of pretty it. But let's have a look. Say the rook. So the rook would be 14. So if we have okay, and by the way, if we just bitwise and this this with 15, this would return us actually 9, because 1 and 1 is 1, 1 and 1 is 1, 0 and 1 is 0, 0 and 1 is 0. So we'll obtain this sort. But let me show you this on the example of, say, this rook. So here we'll have 14. Okay, let me see the white rook code here. White rook, so it's 1110, like this. Okay, so this is 14. So again, if we just bitwise and this stuff with 15, we'll get again like our 14, and this would be white rook. And you might wonder what's going on with the black pieces. So why do we extract codes easily as well, while the number seems kind of a bit too much, but we just ignoring this bit while bitwise ending, so this doesn't affect the result. And if we just, so when we bitwise end say this queen with 15, so here we bitwise end only this part with this certain number, so ignoring the 16th bit, and that's how we can obtain the index. So say the index for the black king would be, so it actually would be 7, right? So 1 and 1 1, 1 and 1 1, 1 and 1 1, 1 and 0 is 0, so bitwise end in this number and this number would result 7. So if we have a look at the index of 7 here, then we will find the black queen. So let's calculate. So 0 1 2 3 4 5 6 7, the 7th index. Here we have the black queen. Okay guys, so I hope this makes sense, because starting from now we're gonna use many these tricks based on the particular piece encodings, and this was just the beginning. So let's actually go on now. The entire engine we're writing this chess programming crash course would contain of the only search function, which would serve 3 different purposes. So generate moves, evaluate the position, and recursively search for the best move so far in the particular position at the given depth. So let's actually start implementing that sort of a search function here. So I can simply say def search, and this function would be taking really lots of arguments, but we'll be adding them along the way. So the very first thing to consider is actually the move generator, and the move generator is going to be pretty similar, well, this is at the very beginning, to what we've done in our print board function. So the move generator would consist of 3 nested loops. So the first loop would be iterating over the board squares, looking for the piece of the site that we're generating moves for. The second loop would be iterating over the move offsets for each particular piece, and the third loop is considered by the leaper pieces like queens, rooks, and bishops to iterate over the particular array they are going through. So again, it's far easier to implement rather than to explain, so let's actually keep writing some code. So the very first thing to consider, we need to define the index variable equals to 0, just like in the print board function, and here we say while index is less than 128, so we're iterating over the board squares, and we also need to increment index by 1. And now we need again to ask, so if index bitwise ended with the hexadecimal 88, which would answer the question if the square is on board. So if this expression is equals to 0, that means that the square we're looking for is actually on board. So from now on we can define the piece variable that would be equal to board indexed by the square. Board indexed by the square, like this. So let's actually now print our piece here. So piece and equals to a space, and just run this. Okay, so somewhat is wrong with the indentation. Hold on a sec, guys. Oh, I just forgot to actually call the search function. Sorry for this. Let's call the search and run the code. Okay, so here we have our piece codes, and again, if we just want okay, so it generates not only the pieces but also the empty squares, but what we need to pick out from this sort of data is basically only the pieces for a site to move. So here let's define a variable called side, and remember here in the piece encoding we had our site definition. So 8 would be for the white pieces and 16 would be for the black pieces respectively. So here, before actually calling our search function here, actually we can specify the site. Well, let's generate moves first for the white pieces. So here I just can simply say that white equals to 8 while black equals to 16. And again, it's really important to bear in mind the binary representation of each particular integer here, so because we're dealing with the bitwise operations. And now the magic regarding this particular piece encoding is coming onto the stage. So now we can simply say basically here if and then we need to bitwise AND our piece with the color, so we don't even need the parentheses here. But actually, by the way, it's regarding the Python syntax itself, you can avoid using parentheses in during writing the Python code, but still, if you use the parentheses, it won't be observed as a syntax issue there. So you can use parentheses whenever you want in Python as well. So just to bear that in mind. So we need to bitwise AND our piece. I'm sorry, just not over here, but actually here. So if piece bitwise ANDed with the site equals to true, so we could have say it like this, but it's pretty enough in Python. It's basically pretty enough just to define this expression like this. So you can add the parentheses, you're free to do that as well. So if piece and site returns true, so in this case we actually want to print our pieces. And let's now execute our code one more time. So here we see that only the white pieces has been printed to the console. So 9 is the pawns and so on, and just so these guys has been printed just to make sure that these are exactly the white pieces. We can do again the same. We can say pieces and use piece bitwise ANDed with 18 to obtain the piece letter mappings here. So we say we are supposed to generate moves for pawns, rook, knight, bishop, rook, queen, and so on. Okay. By the way, of course, if here we specify the black pieces instead of the white ones, we'll extract the black pieces from our board. So bearing that in mind as well. And now, as far as we did implement the loop over board squares, it's time actually to go to the loop over move offsets. So here we'll define the loop over move offsets like this. And actually let's define our loop right over here. So this array consists of two parts basically. So the first part is the move offsets themselves, and the second part is the starting indexes for each piece type in this kind of following order. So, but actually, instead of wasting your time on my explanation, let me better show you how this works via the tests, and you will easily and you'll easily understand actually of what's going on here. So now let's try. Now we need to do a couple more things. So the first thing to consider is actually we need to define the piece type. So I create a piece type variable, and this would be equal to piece bitwise ANDed with 7. Why 7? Because we don't need to bitwise AND with the 4 bits, just bitwise ANDed with the 3 bits is enough to obtain the piece type regardless of color. So that's why we bitwise AND piece with the 7 to obtain the type. And the piece type would serve us as the reference to the particular move offsets. So here in our move offsets array, starting from the index of 30, that is over here. So starting from here, we have the references in the move of sets array for the starting index of the particular piece type to generate moves for. So and in order to obtain one of these numbers, which is again the index in this move of sets array, we need to reference, we need to actually find the type of piece, and let me just show you this. So let's actually break here. So we'll have the only piece, that's also, yeah, print piece. So we have a piece 9, which is a white pawn. If we just print the piece type at the moment, we'll get 1. Why this happens? That happens because if we go to the piece encoding definition here, we see that the white pawn here is the type of 1. So again, seeing white pawn here. So bitwise end on this number with respectively 1 1 1 would so 1 and 0 0, 1 and 0 0, 1 and 1 1. So this would return 1. So bitwise end on 0 0 1 and 1 1 1 would be equal to 1. So just bearing that in mind. And if we now create a variable to keep, well, that's just before creating that sort of variable. So if we actually add 30 to the particular piece type, and let's actually see what we got here. So we got the index of 31, and if we go to our move of sets index, that this is the index of 31, so it's 3 here. So let's index the move of sets. So I say simply move of sets indexed by piece type plus 30. So we should have seen that this 3, and this 3 is actually an index within the move of sets array where to start looking for the moves for the white pawn. So let's calculate index 0 1 2 3. So we are right over here. So just need to add one more index here, and starting from here we'll loop over the move of sets for the white pawn. So that's kind of it. Okay, so what's the particular data which we kind of have to iterate over? So this is the particular move of sets for the white pawns that we're supposed to iterate over along with all the other pieces. So now we have the index of 3, which is 0 1 2 3. So in order to obtain this index where minus 15 starts, we need to add 1 to our 3 and then index the value that we get, use the value that we get to index the move of sets there. So okay, let's go step by step here. So first we need to define the directions variable here, and also say directions plus equals 1 to move away from that 0. So if we don't do directions plus equals 1, so we'll end up here. So but we need get in here, so we need to increment 1 and see that there is a nice cute way of implementing this, but Python doesn't allow you doing that, so we'll go the most pretty straightforward and clear way of doing things. So we're incrementing the directions here. Okay, so also let's bring up this break over here. So I will break, for now we will break the very first piece, and now we need to say while move of sets indexed by directions here. So directions. So while this value is true, we actually need to increment our directions. So say directions plus equals 1. Okay, and here I want to print Okay, so before printing anything, let's store the create a step vector variables. So the step vector would be equals to move offsets indexed by the directions. So let's print our step vectors. Okay, and at the very end I would like to print space. So I hold my breath and try to execute this code. Okay, step vectors is not defined. Step vectors. Okay, so here we did obtain what we actually wanted to obtain here. So our step vectors for the pawn. Well, basically, yeah. Let me just check up the piece. So print piece. Okay, so the piece is 9. That means it's the white pawn actually. So that's because we are iterating only over the white pieces, starting with that starts with the white pawns here, because it's the index 0 and so on. So we start with the white pawns and going on. So if we just specify actually the black color would obtain the step vectors for the black pawns respectively. So here see okay, something is kind of going wrong here a bit. Oh no, it's right. It's just because it's first it goes the rook here, not the pawn. It's not the pawn, it's the rook. So these are the move offsets for the pawn. So we just want to specify the move offsets for the pawn respectively here. So we say if piece, just to show you guys, if piece equals 18, so which is the black pawn. Well, in this case, so piece doesn't actually. Oh, that's because we break here, so you don't have to break. Let's actually print a new line instead. So here we have our move offsets for our black pawns. So let's go back to the white pieces though, and here I just don't want this anymore. So let's now see the moves, the step vectors for all the possible pieces available here. So just execute this one more time, and here we see that the moves being generated respectively for black pawns, sorry, for white pawns, white rook, white knight, bishop, queen, king, the same. Well, because they're actually literally the same. Well, for the sliders, we would need to iterate over the vectors of the sliding ray as well. So, well, that I'll cover that just a little bit later on. So, what I want to say that we actually did successfully iterate over all the possible step vectors regarding each particular piece type that we have here. Okay. Okay, one little thing, so it's better to call this not the step vectors but the step vector instead. Okay, let's just print this one more time. Okay, and now it's time to create the third loop. That would be a loop over slider array like this. So say if so sliders are the pieces like bishop, queen and rook, the pieces that are going along the array square by square. So that's kind of it. And the condition to actually break out of this particular array would be either to hit the edge of the board or capture piece, enemy's piece, and so on. So this would be defined actually. But before that, it's time to define somewhat the most important variables for the move generators. So let's define the variable called source square. Source square. That would be equal to our index. So we're looping over the board indexes. Don't forget that. And the target square would be equal actually to the source square. Just for now, just to kickstart off with something. Source square. And also we actually need to define another variable here that would be equal, that would be named captured piece. So captured piece would serve different purposes, and for now let's init this as the 0. And now let's create a loop while captured piece is equal to 0, and here we'll do all our logic basically. So target square would be incremented by the step vector here, so plus equals step vector. And also we need to specify if and target square bitwise ended with the hexadecimal 88. So if this expression returns true, that means that we hit the off-board square. That's the reason, so we have to just break out of this loop. So we don't need to go any further, and we just can continue with the other pieces, stuff like that. So here we just need simply to break. And let's actually print notation from square and notation target, oh, not the from square, sorry, copy source square and notation target square. Okay, so here we have really lots of moves, and also let's actually do this separator equals to nothing, just to have them in this sort of a format. So actually for each piece, so delimited by the new line we have for each pawns, we have this moves, but you know, like now pieces are kind of going anywhere, which is not the proper behavior, but just let me show you what's happening at the moment. So this pawn now can move here, 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 and also here, 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 along the step vectors. So that sort of behavior should have been stopped by the conditions following in this iterating over the array of the step vector loop. So that's actually so those kind of conditions that would lead to breaking out of this loop is what we're supposed to cover next. And also bear in mind that for leapers like the knights here, so when we have our knight, say over here, we don't really want to iterate the knight to over here and here. Instead we just need to break the loop, and in order to do that we'll be using what is known in NegaMax engine as faking capture. So as far as here, you see that we're using this captured piece variable equals to 0. So as far as if captured piece would be equal to 1, that would be another condition to actually break out of this kind of sort of loop. So let's actually try to implement that as well. Now let's define the captured square variable. So say captured square would be equal to target square. Okay, and also we will need to keep track of the captured piece. So the captured piece would be equal to whatever at board indexed by captured square, like this. And also at the very end we need to make what is known as fake capture for leapers. So an example like pawns, knights and kings. So here we can simply say captured piece plus equals the value of returned by the value returned by evaluating this sort of expression. So we need to say if the piece type is less than 5. So now let's try to execute our code again, and suddenly we see that the pawns here on the a2 b3, a2 a3, and b2, and so on. So we've stopped the pawns from iterating over the squares. So here our pawns now can go only here, here, and here. And let's say let's put a rook somewhere. Then we'll see that this is the d5 square. So e5, f5, g5, h5. So e5, okay, e5, f5, g5, h5, and then it stops because it hits the edge of the board and so on. So we see that the directions for the lippers has been successfully iterated. For the sliders it has been successfully iterated, while the lippers actually break after the very first iteration using that sort of fake and capture trick. Okay, so now we need also to provide some sort of a conditions to break out of this loop if we hit another piece and so on. So that's, and we need to avoid capturing known pieces, and in order to do that, we need simply to say if captured piece bitwise ended with the side to move basically returns true. In this case we need to break out of that loop as well. So another thing to consider here is actually to define somewhat of rules for the pawn moves, and actually here we can simply say that if the piece type is less than 3, which means that the piece type is the pawn. By the way, here when we did fake our piece captures, piece type less than 5 means pawns, black pawn, white pawn, and kings respectively. So that's kind of to bear in mind as well. So this kind of line helps us to capture with the pawn only diagonally, and also do that only in case if there is a piece. Otherwise we should avoid that sort of move. So let me just run this code one more time here. So see, now we have a2 a3, b2 b3, c2 c3, so no diagonal moves at the moment because no piece is standing there. Also let's actually get rid of this print statement, for we don't need this anymore. And just to show you how it's supposed to work, if we'll put on the board, say over here, a black pawn and execute this. So here's a2 a3, which is okay, b2 c3, so from b2 we can capture to c3, which is okay, b2 b3, go in here, okay, c pawn is not going anywhere because there is a black pawn there, and now d2 d3, d2 c3, so d2 d3 here, d2 c3 captures the pawn. So that's kind of it. Okay, and the very last thing left here is actually to define the logic of double pawn moves. So in order to obtain that sort of a feature here, we need to add, so after we've just faked our piece capture here, we need to use this sort of code. And to be honest, only God and Gerd Muller knows what this kind of line of code particularly does. Well, even though I've been doing chess programming for 3 years, I still can hardly understand what's going on here, well, at least not enough understanding to explain how exactly this works. So please reference A.J. Muller's tutorial at his site regarding MicroMax Chess Engine if you want to know somewhat deeper details regarding this particular line of code. By now I just want to show you how this works. So if we just run the code again here, please notice that the double pawn moves were actually generated successfully. So that's kind of the exact behavior that we're supposed to obtain here. From now on, what actually separates us from obtaining kind of sort of ready-made engine is actually to provide the make move functionality with a take back move as well, and that's for about like 7 lines of code, no more. Regarding this particular implementation, and also bearing in mind that recursive mode generator and respectively this search function call would be made as well. And also the evaluation function would be also very simple, just to calculate the material and the positional scores for each piece. And bearing on that, we would actually obtain the best move of the given position. And now I will bring this, I will write a little bit more code. I'll bring this to the state where it kind of works and pause the recording, and when I just end up doing that, I will show you how the end result would actually look like. So okay, so now I edit this code. So in order to make move, we need to clear the capture square, clear the source square, and the target square would be equal to piece basically. And for the take back, the same but in the reverse order. And also, if we're dealing with the pump promotions, defined in this sort of condition, in that case we want to bitwise, and the bitwise or our target square, our piece at target square with 7, which is only to queen promotion. So if we now execute this sort of code, also, okay, just I just need to update my, okay, something is going on here, so just oh, that's because I just didn't yet print the board here. So if we just print board at after making the move, then we see how our program flow is going on. So we're making the move, taking back, making another move, taking back, making move again. So we could have I just print board after making the move, not after taking back, just to have less information here. But if also we print the board over here, we'll see that the move is being taken back as well. So here we actually making all the past possible moves within the position. So this is regarding the make move functionality here. And also we'll need to make recursive calls of the search function right over here where the print board placeholder is done. Okay guys, I've just finished implementing the very basic version of this kind of engine, and let me just show what I've added since what you've just seen basically. So, well, probably, okay, so okay, I already did show this make move stuff, right? So I've added basically what is known as NegaMax search algorithm, and also the evaluation function. And okay, so let's go step by step here. So here let's start with the very beginning. So now we have an extra argument here called depth, so which means that here after making a move, where is our move? Yeah, after just making a move, we're making a recursive call to the search function. This minus is NegaMax specific stuff here, just to turn evaluation scores accordingly. And as far as we hit the depth of the 0, we need to return the position evaluation, and it's calculated based on two parameters, the material score and the positional score. Well, while material score is pretty trivial, so we're using the piece weights array, the array that I'll show you just in a moment, indexed by the piece bitwise ended with 15, just like we did while printing the board. So that helps us to obtain the values for it calculates the material basically, so how many white pieces and black pieces accordingly here. So here is the array, and the mapping of this array is exactly the same like in the case of this one basically, so bearing that in mind. And also the positional score is now calculated by either adding or subtracting board indexed by index plus 8. So basically here I have updated our the right part of our board. So this values represent the scores that piece would obtain if stands on the particular square. So say this pawn, so if it stays on this square, it would gain the score 30. So respectively here. So if it goes here, it would take only 20, and so on. So that's kind of it. And now regarding also have defined a couple of variables to store the best move when the search is actually over, and some Python specific stuff. We need to define the global variables before the search if we want to alter the global variables within the function in Python. And now actually, so yeah, as far as we hit the depth of 0, we just return the evaluation function, and here is the variable holding the best score so far. And actually okay, so and here is the brute force NegaMax search itself. So in case if the score is more than the max score, then we update the max score and store the best move so far. So here we're obtaining the score recursively. So in case if this score obtained recursively is actually more than the max score, which is by default is minus 10,000, in that case we actually storing our best move. And also we can return this temp source and temp destination because they might be of a different color, because well, evaluating the move search tree, it uses it does moves for both for white and black pieces, of course. So we want actually to store the best move here just before returning the max scores. So make sure that all the moves, so they would return the moves of the particular color to move when returning the score. And as you see here, it's the output, so just execute the code here. So we have the score for our particular move and the move of the pawn d2, d4. And if we just increase the search depth, well, as far as this is the free host in Heroku, it's really slow. So, oh, okay, so it even works. Okay, it works pretty nice. So let's increase it even more. Okay, so up to depth 3 is just fine. Let's try the depth number 4. So this would take time, but okay, I highly discourage you guys using probably this depth for this particular environment because of torturing the server itself. So that's not a good idea. So, but still, just to show you that it works. Well, it's not the strongest engine in the world, of course, but it's just a proof of concept, basically. So let's keep the depth of 3, basically, here, and try to kind of play chess. And I'll just show you in a moment what I mean by saying that. So we have the score of 30 and the move d2, d4. So now let's actually try to make this move in our board. So of course, when you write in a real app, you will automate this and provide logic for user input, etc. But this sort of environment is designed for educational purposes, but unfortunately it doesn't have an option to provide a user input, so that's kind of some sort of a limitation here. So let's try. So here is our pawn. So let's try to move our pawn from d2 to d4 as suggested here. And now we need to change the site and actually search the move again. So let's try and doing that. Okay. So we need now to use actually black, and I start the engine again. 15. So b8 to c6. Okay, let's try that move. So b8 b8 to c6. Okay, he puts the knight to c6. Well, not that bad really. So here's the 0 already, and okay, let's actually try now again. So here would be the white, and just execute this again. Okay, c1, f4, so it's developing his bishop here. Okay, let's try to see. It's basically the way b1 to c4, so from b1 from here, so to c4. Oh, no, sorry, just what have I done? No, b1 is here, and from b1, no, from c1 to f4. Okay, so this is correct. So to f4, a b c d e f, 1 2 3 4, and this was a bishop, so 13, like this. Okay, so he's developing our pieces. Okay, let's actually also print the board at the very end, so just to make it clear how the board looks like at the moment. So print board and execute this again. Okay, so develop the bishop, nice. And e2, e4 is now okay. Oh, that's because I just forgot to change the color. Okay, so of course now it's black turn. Okay, so d7, d5. Okay, so let's move this pawn, d7, d5. Okay, so a b c d. Okay, to d5 and change the color and run this. Okay, so d7, d5. Now b1 to c3, so he wants to develop the knight, and so far and so on. So you see, guys, that this kind of engine now can actually play itself. Of course, there is lots of stuff to do, like checkmate detection, which is not currently implemented. There is no peasant captures and castling, and it's the list of what is not available here is so huge that I can't really imagine how big is that. So also at the moment the king could be exposed into check and nothing would happen, so you would just simply capture the king and that's it. So there also some extra logic needed to return the evaluation when king capture is encountered and so on. But you know, like all those stuff, just the details. So you know, like this kind of material being presented in this sort of a chess programming crash course is the very basic to understand how actually the chess programs work in general. So I didn't really set up a goal to create somewhat a strong chess program here. No, instead I just wanted you guys to understand you know, like the logic behind the algorithms of how they work. So I don't really claim this to be somewhat of a complete program implementation, but just wanted to walk with you along the development process of the chess engine development process, and that's basically kind of it. So I have written several chess engines myself, and I would definitely put them into put the links in the description below this video, so you would be able to see the code, download, install, run, test those engines. Some of them even supports the UCI protocol, so you would be able to either play against it yourselves, or maybe just to try to make it playing against other engines as I did back in those days. So I hope you've learned something interesting from this tutorial, and this is it for this video. So until next time, and take care.